So you will see again all the framework of the green function and the pentagon within, but it will be focused more on the practical implementation of this method. So you will see exactly the equations that are implemented in the code. And okay, so you have 1 hour of time.
Okay, thank you, Maurizia. So I'm Daniele Varsano from Italian Research Council and also the European Max Center, which I'm glad to say is the main sponsor of this school. So today, the topic of this lecture is going a bit on the common approximation that enters in a real GW calculations. In the previous lectures, you saw, and I hope you appreciated, the beauty of the glorious Hedin equations. But then now we move from let's say, the Garden of Eden of the theory to the human suffering of a real calculation in our computers. And that's important to know about implementation and about practical approximation that we need to run our calculations, because in this way we also know what to expect for the GW calculation in terms of accuracy, and in terms also of what we can calculate and what we cannot expect to calculate. Sometimes we have a forum with the Yambo Code. You can subscribe, you can access from the web page, and where we used to help users. We have problem, want clarification with the code, that sometimes that arrives questions from user that something like, I'm trying to calculate the quasiparticle gap of strongly correlated I don't know, metal oxides, nickel oxides. This does not match experiment, what I did wrong. This is the inputs, and probably you didn't anything wrong, just you cannot expect to match the experiment resorting on the approximation, on the GW approximation and the current implementation, on the most common implementation of the GW approximation. So I will recall a bit some concepts that have been already illustrated yesterday, also today by Andrea, to arrive to the equation we want to dealing with, and we will see then extensively in the afternoon during the hands-on all the variables governing and to control, to have a meaningful calculations. So we already seen that it's very useful to divide our excitation in our materials in neutral and charged approximations. The topic here, GW, deals with the charged approximation. Tomorrow we will see how to deal with the neutral excitation, with absorption, essentially the excitonic effect. And now, so we are going to look to it. We want to calculate and give interpretation to direct or indirect photoemission experiments. And it's just important to see that essentially conservation of energy and conservation of momentum give access to ARPES experiments, and the process in the systems is to pass from n electron system to n-1 electron systems, and vice versa for inverse photoemission we pass from an electron system to n+1. This is the conservation of the energy, and from this we measure the density of unoccupied states in case of the inverse photoemission experiment. Let's have a look with the workhorse, first the workhorse of the electronic structure calculation nowadays. It is the density functional theory. These are the very famous Conclusive equation of 65 that, that give the success of the theory, because the DFT itself became very useful. It's a theorem of quantum mechanics that became useful. So once we know how to solve this Conclusive equation, all the many body effects, let's say, are contained in this exchange correlation potential, and its glory comes also because of its moderate computational costs. And we know that we have a very good prediction of ground state geometry and the electronic structures. So what about band gap? Probably yesterday you already know the famous band gap problem. And here in this plot from a paper of Mark Schiffsgardner, here we compare experiments of a series of semiconductors which respect the gap calculated in DFT, local density approximation in this case. As you can see that the estimated gap is 1/2 of the experimental one, not even worse than 1/2. This is not a problem of LDA. This is an intrinsic problem of using DFT, at least as difference of eigenvalues in estimating the gap of M materials. This can be also rationalized because, I mean, if you look again here what you are looking at, I mean, from a photoemission experiment where we measure the kinetic energy of the coming electron and incoming photon energy, we see that these energy levels we are interested in are different of n and n-1 electron. And so let's say from here you can just recognize that the ejection or removal of an electron is always a many-body process. And in many-body process in the sense that when you extract an electron from your systems, you are going to extract also the electron hole around your electron. So you have different phenomena of relaxation, screening, correlation. So it's hard to treat as a one electron process. So here comes very useful, that has been already commented today and also yesterday, the concept of the quasi-particle. So the electron plus his screening cloud forming what we call the quasi-particle that will interact with a screened interaction. So anyway, we have just seen that we cannot calculate gaps from the DFT, but this is not exactly true. Just because I mean, the plot I showed before with a very bad agreement, it's the usual evaluation of a gap in DFT when we consider the HOMO and LUMO of a molecule or the minimum conduction band and the maximum valence band. But we can actually write an expression of the gap in this way, performing different calculation of our systems. We consider the system with an electron more, an electron n-1, and we can compute, I mean, DFT give access to total energy, and we can evaluate the gap in this way. This is the expression of the gap indeed, just here, has been rewritten the energy in function of the sum of eigenvalues to the other components that form the total energy in density functional theory. This is the Conscient gap. This is the one that this is wrong, but if we consider all the other terms, here difference of eigenvalues of n+1 and then electrons, etc., the same for the exchange correlation potential and the Hartree potential. Actually, here this is a set of molecules, and we can see that, okay, this is not perfect, but the agreement is not that bad. The problem now is, so why we want to go to GW, many-body, when we could calculate gaps with density functional theory, which is much more feasible, is that for periodic solids, adding an electron or removing an electron of the system is not feasible. I mean, because we are dealing with a bulk, we have a unit cell, and a repeated unit cell in the space, usually in plane waves when we treat with bulk, and in periodic solids, this operation, this kind of calculation is not feasible. So this is why, as showed by Andrea 1 hour before, the green functions is the central variable that naturally contains as its poles the excitation energy we are looking for, exactly the quasi-particle excitation energy, exciton lifetimes. Just to mention here, I will show some at the end of the lecture, some example. Using a green function theory, we have also access to total energies and to any expectation value of one particle operator. So it's very powerful, this the many-body perturbation theory and the green function method. So this was already shown by Andrea. This is the definition of the Green function, the propagation, I mean the creation of an electron at a time and position at T2, T2. We propagate in the system for a time T2 minus T1 in an interacting Hamiltonian. We annihilate, and this is the Lehmann expression, and it can be easily shown that these EJ here, the poles, are exactly the many particle excitation energy we are looking for. Okay, now how to obtain the Green function, how to calculate the Green function. We are in many-body perturbation theory. Let's say that we start from something that we know how to calculate, we approximate it, something that we manage to calculate, and which we evaluate what is not known, hoping that the difference is small. So let's say we know a G naught, usually a non-interacting Hamiltonian. H naught you can already imagine, I mean you saw also yesterday in the class, which is our starting point. G naught is usually the Green function of a density functional theory calculations. We add an interactions, and this is the definition of the self-energy. Everything is unknown of the interacting system is put in sigma, in the self-energy. Okay, so from the equation of the motion of the Green function, we can arrive to these equations, and if we know the self-energy, now we arrive to the definition, I mean the approximation of the self-energy, we arrive in the Lehmann representation to the Quasiparticle equation. This is the equation we want to solve. This is the Dyson orbitals, this is the self-energy. As you can see, I mean, written in this way, naively, one can think about some similarity with the Kohn-Sham equation, but important difference, conceptual difference, is that self-energy contains many body effects as the exchange correlation potential in DFT, but here this is the potential of a fictitious system. This is the real potential felt by the added or removed electron from the system. The self-energy is not Hermitian, is non-local, it is energy dependent, so this complicates a lot the solution of the equations. And then, as highlighted by Andrea, here the FS are not normal, and the energy here are complex, so it's much harder than a density functional theory calculation. Okay, how to obtain now the self-energy? This is the pentagon already shown by Andrea. This is the very famous Hedin equation. I would say that it's quite impossible to solve self-consistently. We can try to iterate, and we start from G equal G naught, so independent particle calculation. We know how to calculate the Green function of this non-interacting Hamiltonian. We start just setting the self-energy equal to 0, so this means then that the vertex is discarded, is neglected, equal to 1, and we arrive to the equation of the GW approximation. So sigma is exactly GW. Here we have the expression for the polarization, where we have neglected the vertex, and here we have a Dyson equation for the Green function, and another Dyson equation for the screened electron potential. Okay. Note, it's important to, when we talk about GW, so approximation is that the vertex has totally neglected. So it means that the GW cannot provide, there are cases where it cannot provide the right solution. And here, this is another important approximation that is usually done, not always. Here, as G, as Green function of our systems, we consider the non-interacting Green function, G naught. Okay, so G is the Green function of the non-interacting systems. This is the expression of our self-energy. In time, by Fourier transform, we have here an expression in frequency domain, and for what concerns W, this is our Dyson equation for the screened electron potential, and here the approximation G equal G naught, we have also an expression for the polarization function that will be G naught, something that we can indeed put in our codes and calculate. So, first step is to solve an independent particle calculation, for example, an LDA or any other flavor of density functional theory, and we can build in this way, this is the expression in real space of the polarization that is made of non-interacting electron and holes, as shown here in this diagram. With this choice of the polarizations, here we arrive, this is the expression of the screened potential that obeys a Dyson equation, as was shown by Andrea yesterday. It can be seen also in a classical way. So W will be the potential plus the potential felt here for a test charge to induced density by the perturbations. So here we say that the induced density is such that the system responds independently, as an independent system, to the total potential, not the external potential, but the total potential, the external plus the induced, and this is indeed the random phase approximation. And this is an approximation. So here we can see with this choice of P, this is the diagram, the infinite diagram that are included in the polarization, so the bubble approximation. We have P is P naught, G naught, G naught, and all the bubble diagrams are included. So we have seen now the sigma GW as a G naught consham W, and usually this is what is done in practice is to divide the self-energy in two pieces. We are just adding and subtracting the Bayer column potential here, and we arrive to a definition that what is called exchange self-energy and correlation self-energy. This is something we will see, we will calculate practically this afternoon. This is the expression in real space, and this can be integrated in the frequency domain analytically, and we arrive to the expression of the Hartree-Fock exchange term. This does not depend on the frequency anymore. This is a static term, and here it is the expression for the correlation potential. The presence of W with this frequency dependence, it made it computationally demanding, and this, you will see, it is the most consuming part of our calculations. So, practical implementation of these equations. There are many codes in the market. Many of them use the same approach in terms of basis set. This is the reciprocal space and frequency domain. Just to mention, I mean, this is the Yambo Code, the implementation of the Yambo Code, but there are others, famous code as ABINIT, as GW Berkeley, and probably many others I forget to mention, but it's not the only recipes and the only standard, the only implementation we have. There exist many codes, real space and real-time implementation by Godby and Richard Neitz. Use of localized basis set, that is very convenient when dealing with finite systems, let's say molecule clusters, because you use localized sets, and this allow to be very performant in the calculation of integrants. Here there is the Rolfing code, I don't know the name, but there is the code of Feliciano Giustino, the Fiesta code, where also Claudio, that is here, is involved. There is the code of Fabienne Bruneval, MOL GW. They are very performant, but I mean, they are meant for localized systems, for molecules, and not for bulk system solids. Then other implementation, Paolo Mari make use of localized Magnet function. Surely I forgot many of other codes. And now we stuck in this reciprocal space frequency domain implementation. This is the expression that are coded in Yambo in plane wave set. Just the expression before we have developed in plane wave. This is the exchange part of the self-energy. These are the oscillator strengths. This is the correlation part, and you can see that we have to manage with the frequency integral here of the epsilon minus 1 with the frequency dependent. And so also we have seen, we have to arrive to this expression, we have done already several approximations. So we are talking now to what is called the G naught W naught. So it means that the Green function is the G naught from the DFT calculation, from the and the W, also the polarization has been calculated as G naught. So even at this level, let's say the basic level, the calculation is rather laborious. Here I start to mention some important ingredients that should be checked when doing this kind of calculations. For instance, here we have an integration of the Brillouin zone. That means that we need a converged k-point sampling, which is not the same convergences that we achieve for a DFT calculation, should be checked exactly for the calculation of this kind of integral. Here we have a sum over unoccupied states. Here it enters a closure relation, so this summation in line of principle infinite, and something that should be checked carefully in order to obtain meaningful results. I mean, this is the basis of the best practice of GW calculation. Otherwise, I think you can get whatever if your parameters are not properly converged. And here, the most complicated part, maybe I would say, is the integration in the energy domain. This is just the slide you have in your cheat sheet, just what I already said here for the sigma exchange integration of the Brillouin zone, some occupied bands, and here there are the name of the variables that governs the convergence of these expressions. Here the same about the correlation part of the self-energy. Now, let's have a look to this integral in frequency domain. In principle, you can calculate this numerically. This can be done, but you need to converge. I mean, in a simple way, you need to sample. So you calculate your RPA dielectric function matrix for a lot of frequencies, then summing, in order to have the integral. This can be done. Actually, Yambo can do that. It's very cumbersome. And usually, this is done in many of this code, and also Yambo does, make use of an approximations. We model this matrix. Each element of the matrix can be modeled. Usually, we have the imaginary part of epsilon minus 1, the macroscopic content, it's excited sharp peak, I mean, the plasmon peak. So we can do, in many cases, the bold approximation that our function is a peaked function around its plasmon peak, its plasmon frequency. So we can model this is the expression that you use to model. It is a one-pole, just one-pole wave function. We have to calculate the residual and the pole of this of the epsilon minus 1 GG prime. Once we are able to do that, then this integral is analytic. How to evaluate how to evaluate these parameters, here, let's say, there are many recipes in the literature. Here some reference, Ibersen-Lewis, Godbinitz, Engel-Farid. What Yambo implements is the Godbinitz recipes that means essentially to perform a calculation for two frequency, usually the static value omega equals 0 and to a complex frequency, which is an input of our codes or our calculation, and then this is the two equations in two variables. We get the two value, and we can plug here in the analytic expression of the frequency integral. Here I want to show just the performance of different different recipes for the Plasmon-Pole approximation, in particular this Ibersen-Lewis. Ibersen-Lewis, a difference of the Godbinitz, consider the static limit, but then the coefficients are evaluated through some sum rules of the epsilon minus 1. Here you can see that this is the real part along the real axis of the epsilon minus 1 of the screening for silicon, diamond, zinc oxide, and metallic neon. And in the case of silicon, everything is similar. Here you can see some difference. And here is the impact of different approximations. GN is the Godbinitz, this is the Ibersen-Lewis, here other models. This is the reference, it is the numerical calculation of the self-energy. So calculating for a number of frequencies. So let's say this is the reference and this is the experiment. As you can see that beside the silicon everything works perfectly. For other systems, big difference arise. Let's have a look, for instance, to the zinc oxide. Here we have the Godbinitz that differs by 0.01 electron volt from the reference. Here the Ibersen-Lewis seems to be much poorer in this sense, but note that Ibersen-Lewis that has been widely used somehow is more, in many cases, is approach better the experiment, but this is, I would say, an artifact in the sense that the reference here is the reference here is the exact computation of the integral over there. Here, in the case of zinc oxide, there is a nice work of Marty Stankowski, where analyzed in details the performance and the convergences of different models. Anyway, this is the accuracy that we expect from the Plasmon-Pole approximation. So, remind, this is another approximation that entered in a calculation. It's a bold approximation. In many cases, well, actually not so many, but in some cases, the Plasmon-Pole model fails. For instance, interfaces. For instance, there is a work by Andrea on the electrons in copper, where it is shown that the Plasmon-Pole approximation is not suitable. And in this case, full integration is needed. And there are also other methods to perform the integral, the contour deformations, alternative methods. And here there is Dario. There is a poster of Dario that actually is working on a multiple expansion of the dielectric function. And there are some preliminary results on that. So we have Plasmon-Pole, you need calculation of the screening matrix for two frequencies, a direct integration, hundreds of frequencies. So you can imagine the computational costs. Other methods are contour deformation, 20, 30 frequency, I would say, something like that. And now we are exploring an intermediate regime to deal with this integration. Okay. This is again a slide taken in the cheat sheet that is what are the input variables governing the Plasmon-Pole. So what do you have to care? Essentially, you always calculate the static limit, you calculate the electron matrix in this PPA energy fixed here, and of course, so you need a converged calculation of your matrix for these two frequencies, and these are the variables. Again, the dimension of the matrix here, Gg prime. This is the RL stands for reciprocal lattice. You will see this afternoon. You can also give a cutoff in energy. And here, the number of bands in the summations that you need to converge. I mean, the electron hole pairs you have to include in your polarization. Okay. Now, once we see how to calculate G naught, we see the W naught also in its frequency behavior. We want, again, solve this equation. Here, we assume that our Dyson function are our Kohn-Sham integral. This is another approximation that enters in the calculations. So, with this approximation, now we can solve this equation, the quasi-particle equation. This is a nonlinear equation. What we can do is either develop around our Kohn-Sham eigenvalue and solve at first order. This is what usually done. In Yambo, there are other alternatives at the second iterative method, just iterative method to find the root of our expression of our function. Okay, so we have all the ingredients in place, and we can arrive here to what we want to calculate, that the quasi-particle energy of our system. I want to mention here an algorithm implemented in Yambo, developed in the group of Xavier Gonza. When calculating the self-energy here, we have a summation over unoccupied bands. This could be very painful. I mean, you have to calculate include many bands in your summation. This means also that you have to perform a non-self-consistent calculations with many bands. Many bands could be thousands of bands. This algorithm that we named in the code terminator, but I think that this is our jargon, consists simply in, it's very simple to understand, and let's truncate our summation to a certain band, this big NB, and let's see what is missing. I mean, well, what is missing from the other bands we are not including. And we do an approximation, the extrapolar approximation. We assume that all the states above this high number of bands have the same average energy epsilon sigma. Making this approximation, now we can exchange here the order of the summation, and we can calculate here what is missing from the summations, and so we can correct the value we obtained summing up NB to these corrections, and as you can see here, these accelerate a lot the convergent with respect to the empty bands entering in our calculation. This is the conduction band maximum and the valence bands minimum for bulk silicon. This is a cluster, I think, and without this correction, you need more than probably 1,500 bands. Here they are already converged with a half of this number of bands. This is the valence band maximum for a titanium dioxide nanowire, many occupied bands. This is the calculation without opting any correction. Here adopting different correction, just playing with the value of the extrapolar that we have introduced in order to collect all the transition above that energy. And this can be also tuned to achieve here a speed up, a very important speed up. What happened in a GW calculation when we deal with non-periodic, not strictly three-dimensional periodic system. If you want to calculate a nanostructure, an isolated molecule, a nanowire, a wire, a polymer, a carbon nanotubes, a 2D systems, a slab. So two systems, they are non-periodic in some of the directions. This is a plane wave code, so our representation of the systems is always replicated in space. We are always dealing with an array. And the GW calculation, I mean, really feel the long range interaction. And so the naive, the first thing that comes in your mind, this is a problem that you have also in a DFT calculation, if you want, is to enlarge more and more, so putting more and more vacuum in the non-periodic direction. Unfortunately, the convergence with respect to the vacuum is very slow, and the scaling of the code of the computational cost, putting more and more vacuum is very bad. So here is just a representation. This is a bulk in 2D, this is a wire 1D, this is an isolated molecule, where I repeat also here the bulk, the supercell sites. And there is a simple idea that do not treat, I mean, to modify our Coulomb potential. Our interaction will be not 1 over R, but will be 1 over R until a certain threshold, and then will be 0. This setting properly the value, I mean, the definition of this domain with respect also to our supercell sites permits to speed up the calculations with respect of the vacuum. So this is our expression. We are dealing in a reciprocal space, so we Fourier transform these modified Coulomb potentials and for some definition of the domain, of the region. This is the case of a sphere for a molecule. You can put in a sphere, and this is you end up with this analytical expression. This is more complicated in the case of a cylinder. These are Bessel function that comes here. This is the Wigner sites for a 2D system where we cut to the Wigner sites of our supercell. These are the references where they're explained in detail. Care has to be taken to the limit for Q equals 0, G equals 0 of this potential. Here you don't have any problem, but here you have divergences that are not anymore 1 over Q squared, but 1 over Q in this case. It is logarithmic in this other case that you should take some caution when dealing with the limit with Q equals 0. That's when you're interested when calculate optical absorption. Okay, here is an example. This is a 1D system. This is an atomic chain. Here you have the interchain distance. Here is the supercell volume. As you can see, the gap here, its point, show a very, very slow convergence with respect with the vacuum. The modified Coulomb potential allow you to converge much faster. I think you will see some application of this tomorrow in the calculation of absorption spectra. Okay, let me summarize what is the workflow of a typical GW calculation. We always start with the DFT calculations. This is something you have seen also yesterday. The first step is always a DFT calculations. And this provides us Conchamp eigenvalue and eigenfunction. Both are used to calculate our polarization, our green functions. The polarization then is used to calculate our screened potential, usually done in a Plasmon-Pole approximation, even if it's not mandatory, but if it can be done, it's very recommended. We build up the self-energy, and then we can solve our quasi-particle equation and extract the quasi-particle energies. Okay. So, as shown by Andrea before, GW, in many cases, semiconductors, works, or at least provide a very much better agreement with experiment with respect to the DFT calculation of the GW. So we have a huge improvement with respect to LDA. In some case, the agreement, I would say, it's perfect. This is the case of diamond. This matched the experiment, but for the wrong reason. Maybe Andrea, I think, worked on exactly on diamond effects of, I mean, so don't be scared if you don't match the experiment, but don't be so happy even if you match, because it could be the wrong reason, the matching with the experiments. Here other effect enters, so there is no, the story is not just the GW calculation that explain the gap of the diamond also, because it varies with temperature. Metals. We have talked before about semiconductor. Here metals. Also for metals, with some care, we have a very good matching with the experiment, with the photoemission experiment. Much better than LDA. Here it's important to note that in the case of metal there is a breakdown of the Plasmon-Pole approximation. This is a work by Andrea of 2002, and here had to resort to full integration for obtaining the self-energy. Here, if we can define here a local potential from the GW, this is a metallic surface, aluminium 111, and it can be seen that the GW is also able to catch image potentials. Image potential, I mean, this is a polarization effect, and it is catched by the GW approximation. As I told in the introduction, in the first slides, we can also calculate total energy using GW. I mean, we have the Green function. With the Green function, we can have access to total energy. Here is the sample of three-dimensional 3D electron gas. This is a work by Pablo Garcia Gonzalez and Rex Gobbi, where they showed here that the correlation energy here of the three-dimensional electron gas at high density, a smaller s, the GW approximation, but GW, this is not G naught W naught, I mean the self-consistent one, not the vertex, the self-consistence in terms of GW, provide a perfect agreement with quantum Monte Carlo calculation. As far as I heard, this is not a final story. I mean, there are works, I mean, there is Tommaso that is also working on that, and maybe you don't agree totally on this perfect agreement with, well, we have also Mike here that is a quantum Monte Carlo guru, and so probably this perfect match is not the final story.
There are two papers in 2016 and 2017 by Optical and Cotillard, and the other one is from a Russian guy that I cannot remember the name, that says that actually the energies from their calculation are a little bit off those results. Though by off I mean this, between the second and the third decimal points in upper units. I don't see
No, okay.
units here, but
Yeah.
so this is
okay. Here another work about the Rex Gobbi, Pablo Garcia Gonzalez. This was a slab of gallium. They show that the GW is also able to match, I mean, to represent the van der Waals interactions. Again, on total energy, here, very briefly, there are works that also calculate here lattice parameter, for instance. Here we can see that lattice parameters in GW is quite good. This is self-consistent GW. Quite good means that, I mean, it's not better than GGA anyway. But we know that GGA is the workhorse for this kind of calculations. So we have good energy here, but the same foot when you calculate the electronic properties, the electrospectrum, we can see that the self-consistent GW is worse than the simple G naught W naught approximation. So that's not always the self-consistency here is better than G naught W naught. Remember always that you have neglected the vertex. So that could be important. Optical absorption, if we, this is the silicon, I think will be shown tomorrow in many flavors. This picture, we have the experiment, we have the RPA absorption. If we just plug GW energy, this does not the job. I mean, it's not, it's here in this case, it's just a read shift, so something is missing in the description of the absorption. That will be the topic of the theoretical and the practical lecture of tomorrow. So some important ingredient is missing, and we will have the lecture by Maurizia and Fulvio addressing this point. So I write to some conclusive remarks. GW, many virtues. Parameter-free method provides accurate results, quasi-particle energies, also total energy, also provides information on lifetime of the excitations. It is the starting point for optical absorption in many-body perturbation theory. As you will see, that quasi-particle energy are ingredients entering in the solution, in the build-up of the beta-salpeter kernel. And G naught W naught, I try to show you that even in its simpler flavor, it's a quite complicated calculation, it's a quite complicated workflow. But I mean, a virtue of this kind of calculation that the algorithm is suitable for HPC computations. So they scale very well if well implemented in modern machine, different architectures. Just to mention, Yambo now works also on GPU accelerators. So if your results don't match the experiments, take a message. Before asking to the forum what I'm doing wrong, check carefully your converged parameter. I call this this boring part, but we will have a lecture just now addressing also how to make machine work for you for this this part of the calculation. It's just repeating your calculation, increasing parameters. Even at G naught W naught, again, several converged parameter and approximation have to be checked. Here, just the sum of the ingredients we discussed now that should be checked, that you will see. And also, I didn't mention Yambo, as many other plane wave codes are make use of pseudopotentials. So you neglect core electrons. These have an impact also on the W calculation, and this is something that should be checked, also in terms of how many electrons enters effectively in your calculation. So if your system needs to treat explicitly semi-core states, this has an impact in the calculations of the quasi-particle energy. So don't forget that GW is in approximations, so it's not the final story. This is already mentioned by Andrea before. And something that I didn't mention, but you can understand, G naught W naught is not self-consistent, so you always can have a dependence on your starting point. And like a rule of thumb, if your starting point, your DFT starting point is more close to what you get, then the GW connection will be more accurate. So it's not independent of the DFT calculation behind the G naught W naught. This is important for molecule, and in Yambo now it's also possible to do a GW calculation on top of a hybrid calculations. even in partial self-consistency, essentially we mean eigenvalues only self-consistency. So you calculate your quasi-particle energy, and this quasi-particle energy are then used to build up again the screening and the green function. So a new self-energy and iterate. Usually it converges very fast. In this way, the problem of the starting point is mitigated. It's not resolved, but it is mitigated. But anyway, about the wave function, you always assume the initial constant wave function. So here there is still a reminiscence of the starting calculation, RPL level for the screening, and Plasmon-Pole model. Plasmon-Pole model in particular can be critical for several materials. So this is my final, so I would say GW is successful interpretation of spectroscopic properties of many systems, but it relies on many approximations that can also fail. So I would like to thank the sponsor that funded this school, so the Max Center of Excellence, the Psyche Network, and the ECTP. Okay, I would like to leave here some reference. These are the seminal paper of the Hedin's equations we have seen before. Here are some reviews, and I put here just two very recent review that appeared last year and this year on GW. It's kind of compendium that I found quite useful, and these are the two papers on the practical implementation in the Yambo code, and I thank you for your attention.